All right, thanks for coming, everyone. So let's get started. My name is Renee. I'm a software engineer at PagerDuty, where I've worked for about 2 years. I work in a team that works on some really interesting projects on everything from front-end UI overhauls to behind-the-scenes database optimization. And it's actually my first experience with anything even close to DevOps related and working with a distributed system. So anyways, let's just get right into it. Some of you might be wondering, what's PagerDuty? PagerDuty is an incident management platform that integrates with infrastructure monitoring software to improve operational reliability. Services like New Relic and Datadog integrate with our API to provide timely notifications to users when their infrastructure performance deviates from their user-defined thresholds. So when one of these monitors sends a request to our Events API, it kicks off a series of operations in our network of distributed services, first through event processing, and then creating what we refer to as an incident, and then finally through to our notification system that interfaces with services like Twilio and telecommunications providers. So today, I'm here to talk to you about an engineering initiative I developed, the nuclear option. The nuclear option is a scaling adjacent project that originated when my team was planning the scaling work needed to support a new traffic profile that we predicted was going to be several times larger than anything we had historically had to deal with. So two of the questions that we needed to answer were, what do we need to get done, and how do we know when we're finished? Now, when it comes to making new features, these questions are relatively easy to answer. But in this case, the answers weren't as obvious because while we can measure the capacity of individual parts of our system, the capacity of the system as a whole is not a simple sum, but rather it's a function of all those different parts. So one problem, for example, my team has been trying to address is our web application's incident dashboard. For the average account, performance and usability are not usually an issue. So essentially, a PagerDuty account consists of users, services, and incidents. However, as accounts grow across these dimensions, the relational complexity between the different parts of our application can skyrocket. We anticipated that users on a very large or very active account would begin to experience degraded performance, which would only get worse over time as other accounts grew larger and more complex. So given known incident creation rates from our most active account, we expected an exceptionally large account to create up to 20,000 incidents per day, or 600,000 incidents per month, and that translates to about 7.2 million incidents per year. So aside from the problems of processing rapidly incoming events and making sure that our data stores can keep up, one of our biggest challenges was simply how to display all of these incidents. So, for example, if we're struggling to sort 100,000 incidents by status or origin, trying to do the same thing with anything even approaching 7.2 million is a one-way ticket to Timeout City. So let's get back to those two questions that we were hoping to answer. So part of the answer is the nuclear option. Half science, half hold onto your butts. The nuclear option essentially consists of creating a large number of events associated with a single account, testing existing hypotheses, and generating new observations. But that's crazy, right? Why would we ever expose our production systems to that kind of abuse? Why wouldn't we just do it on a development environment or staging or something? Well, the most obvious answer is because those test environments aren't going to be the ones handling our new traffic profile. No matter how carefully and painstakingly you try to reproduce your production environment, it's still not the same. Furthermore, maintaining a load test environment, it's inefficient, it's expensive, not to mention it can be a maintenance nightmare. Whether it's a slight change in configuration or maybe a difference in database drivers or maybe it's even something completely out of your control, the only thing that's going to act like prod is prod. So before I worked at PagerDuty, I actually had no idea that engineering organizations took this kind of approach to building and maintaining resilient infrastructure. And to be perfectly honest, I had no idea what DevOps was. Wah, wah. In any case, during the process of researching this talk and just doing my day-to-day work, I learned about Netflix's Simian Army, which is what they call a suite of automated tools that they use to stress test our infrastructure so engineers can preemptively identify and fix points of weakness before they become a problem. I also learned that this kind of methodology has a name, chaos engineering. Chaos engineering is the discipline of experimenting on a distributed system to build confidence in that system's capability to withstand turbulent conditions in production. It's an empirical, systems-based approach that addresses chaos in distributed systems at scale and under realistic conditions. So at PagerDuty, we actually apply principles of chaos engineering and learn about the behavior of our distributed system during weekly experiments that we call Failure Friday. Oh, there's a cap on my water. I was trying to drink that. So nearly every Friday, engineers from across the organizations get together for an hour while we deliberately expose our production servers to controlled and predictable failure scenarios. So anyways, what does the nuclear option have to do with all of this? Well, the nuclear option is an ongoing series of these Failure Fridays that are aimed at surfacing bottlenecks in our event and incident pipeline, specifically within the context of high load being generated by a single account. The idea is not so much to test the services themselves, but rather the edges where those services interact. So I tend to think of the different parts of our infrastructure as tanks joined by tubes of various sizes, and the goals of nuclear testing are to discover both spillover thresholds and leaky pipes. So at PagerDuty, our culture of reliability has resulted in several tools we can use to anticipate and design for failure. However, the way that we run Failure Fridays didn't seem holistic enough to give us the information that we were looking for. So Failure Friday largely focuses on testing a single service by stopping and restarting processes, applying latency, and ensuring that our failovers and backups kick in as we expect. One of the things that differentiates nuclear testing from our regular Failure Friday is the inclusion of every team responsible for the incident pipeline, all of whom are monitoring their services as we ramp up the load on the entire thing from beginning to end. So although we design for as many use cases as possible, sometimes our mental models can break down at a very small scale, or in this case, at a very large scale. Nearly every engineering team had a few JIRA items in their backlog related to scaling our application, but overall it looked like a really short list. I was like, really? All we need to do was finish one or two tasks and we're ready to handle the potential load generated by, a bunch of new enterprise accounts? I was rather skeptical, and I always try to keep in mind the optimist adage, hope for the best, but plan for the worst. So let's get back to those two questions. Question one, what do we really need to do? As I mentioned before, we already knew that some bottlenecks existed. These were mostly identified during major incidents and are often addressed through regular operational work by individual teams. The most worrying part of this whole thing was not so much the work that we already had planned and that we knew we needed to do, but rather the work that we didn't know we even had to plan for. So part of the motivation behind the nuclear option was to surface issues with the incident pipeline that we hadn't even considered or wouldn't even become apparent except under the specific load generated by a single account with a lot of activity. So question two, how do we know when we're really done? So the danger of optimization is that it's the kind of thing that's never done. There's always some code that we could refactor, some services that could be made more performant, and I bet there's a ton of us that would be perfectly happy sitting with our heads down, perfecting the systems that we have right now. But we have to balance business and engineering interests, otherwise we won't be able to pay our bills. And although we can't tell the future, we can make an educated guess based on a combination of historical data and estimates of how many users, services, or schedules that we'll need to support. Essentially, once we run a nuclear test without any problems, we're probably well equipped to handle our projected increase in traffic. So yeah, we could make sure we could support 3 or 4 times that traffic profile, but when would we ever get to the really fun projects, like rebuilding some of our oldest, most fragile, least tested legacy code? So when this initiative was first conceived, I didn't have a concrete idea of what we'd actually be doing. So what would a test look like? Would we do it during a Failure Friday? How are we even going to generate the kind of load that we're looking for? Fortunately for me, because we've had so much practice poking holes in our own infrastructure, I didn't have to start from scratch when looking for the answers to those questions. But it was surprisingly difficult to articulate exactly what we were trying to accomplish. What defines the new access patterns of our large accounts, and how could we describe a framework we could use to conduct these tests? After countless hours spent whiteboarding and scouring our internal wiki, I had all but given up on finding any answers to these challenges. Like a raccoon washing its cotton candy, it seemed like every time I came close to an answer, it would evaporate, leaving nothing but sadness and bad metaphors. Ugh. So I was running out of time and Red Bulls and other sources of caffeine when the answer finally came to me. Science. The answer was there all along. In the scientific method, which we all learned about in like grade 4, but the scientific method turned the nuclear option from a nebulous collection of ideas into something that could actually be executed. So now let's go over how each part of the scientific method was applied to the nuclear option project. So our purpose. Our purpose was to find bottlenecks that would be exacerbated by, find bottlenecks in the incident pipeline that would be exacerbated by the traffic generated by a very active account. So by proactively addressing potential points of failure, we don't rely on our customers to find bugs before we do. So if failure is inevitable, we may as well make sure that it happens on our own terms during business hours, when we're awake, and when there are snacks readily available. Research. So I wasn't too surprised to find that there was already a load generation tool developed by PagerDuty engineers called Scale. Scale creates bogus accounts, users, and notifications in order to simulate load on our entire system. However, there were a few impediments to using Scale for this particular series of experiments. First of all, Scale generates load across a large number of accounts, whereas we were trying to identify the points of weakness exposed by traffic on a single account. So we could have created a new load profile, so I don't know Scala, and making a new profile for Scala isn't trivial, and it seemed like a risky endeavor to invest that much time only to end up with something that wasn't actually what I wanted or needed to use. And finally, Scale is still directed at our load test environment, which we all agreed is not a reliable mirror of prod. In order to get an accurate picture of what would happen under high account-specific load, Scale would need to be modified for use on production, something that is unfortunately also non-trivial. Last year, however, my team had conducted experiments using a load generation tool written in Node. And the advantages of extending this tool is it's highly configurable and can target either a production or a development environment. It can be quickly iterated on during testing without a lengthy build process. So during some of the tests, we noticed some aberrant behavior or even some bugs, and we were able to fix them on the fly. And using functional reactive programming, the concepts there seem to map really, really well to the time-sensitive and continuous flow of events through our application. And finally, it's written in JavaScript, which allowed for fast prototyping and just getting things rolling as quickly as possible. All right, hypotheses. We're getting to the experiment, we're getting there. But first we need some hypotheses. So any one of our engineers knows what happens when major stresses, such as this year's S3 outage, are placed on our pipeline. However, what, if any, would be the difference in the effect to our infrastructure if all the events were associated with a single account? Would our throttling system or our rate limit save us? Because functional ownership of the incident pipeline is distributed among several engineering teams, each team was tasked with coming up with their own hypotheses, and which would be verified or refuted by observations. So now we're on to the exciting part, the experiment. Ideally, each nuclear test would have consisted of several iterations of a standard process. So first of all, each team would verify that their services were working as they expected, and then we'd note any changes to overall system performance as we ramped up the load and started flooding our system with events and calls to our API. Each team, in broad strokes, would record any measurable changes from the previous iteration, and then we would see if there were any changes to the user experience in our web application. We had a test account set up in advance of the first test, and each subsequent test was targeted towards various parts of the pipeline through specific account configurations. All right, analysis. This is where things get interesting, right? So to date, we've run 3 nuclear tests, and each one went exactly as planned, from developing a load generation platform to setting up the testing account to actually running the experiment. It was awesome. It was a dream. Just kidding. And you knew I was kidding. I really hope none of you believed me, because despite everyone's best intentions and well wishes, Of course, the experiments didn't go as planned. So the part of me that follows Instagram accounts with like sleepy kittens and like birthday cakes, the part of me that doesn't own an umbrella, I think that part of me actually believed that everything would go to plan, that the code would work perfectly, that all our services would respond exactly as we expected, and we'd close off each test saying, wow, Renee, way to like hella build something up that isn't really a big deal at all. This is so boring, yawn. But that's totally not what happened at all. So today I won't get too far into the weeds, but I'll just share some of the things that went well and some of the things that went not so well. So let's start off with the things that went not so well. Buggy load generation code. Ugh. Engineers from other teams, since then, they've contributed to the code base, and we now use it as an incremental testing tool for things like query optimization. However, before it was adopted as a bona fide project, it was basically a side thing that I did on my own in the office kitchen after work and on weekends. So as a result, it didn't have the advantage of collective expertise and experience and basically just like code review that it has now. Multiplication. Multiplication, as I discovered, is key when it comes to conceptualizing our systems at scale. So when I was working on the platform, I made sure that each part worked at a small scale. For example, retrieving 100 service keys from our API, or generating 5 or maybe even 10 event streams and tracking the results. What I didn't anticipate, however, was how things like wait time and asynchronous behaviors would be magnified and exaggerated once the platform was being used to generate load over thousands of service keys or making thousands of API calls. So this translated to issues like slow spin-up time. So we're all sitting around waiting for the experiment to start, and we're tapping our feet. So Renee, when's it going to start? And like, guys, it's spinning up, it's spinning up. And this also led to higher than expected rates of event generation. Operational load and customer impact. So the first 2 tests, unfortunately, resulted in moderately severe service degradation. And not only did this have noticeable customer impact, it also increased the workload on another engineering team, like my friends, my colleagues, the people that I work with and see every day. And these people were already experiencing a great deal of operational pain. We had anticipated a bottleneck processing outgoing notifications to customers, but we had no idea the backup was going to be as bad as it was. And finally, the Titanic had a bunch of tanks too. So I'm mostly going off what I remember from the horrible, horrible movie, but her engineers were convinced that the Titanic's separate bulkheads would prevent it from sinking. So likewise, even though we apply throttling limits and even though we apply throttling and rate limits to our individual API users or individual API keys, we still observe performance degradation because downstream services weren't able to process the backlog of events quickly enough. So what I'm saying is, even when we can prevent local failures, we still need to take a wider view when designing resilient systems. All right, so enough with the bad news. Let's get on to the things that went well. Cross-team communication. With so many teams making up the incident pipeline, sometimes we don't all get together and talk as often as we should. So one goal of this project was to ensure that it would benefit all the teams that were part of the scaling initiative. So they all needed to be included when planning and executing each test. So I got to know a lot of my colleagues a lot better, and I have a way better appreciation for the specific challenges that they face. We have a nifty, friendly, approachable load generation platform. So aside from learning a ton about everything from Datadog to Splunk, I figured out how to node, I learned a great deal about functional reactive programming, and so have the other engineers that have extended the tool. Since then, there's been a lot of refactoring to make it modular and testable and even easier to extend. And finally, we have a resource for ongoing testing because of the leftovers from our experiments. So we can use these giant Leviathan-esque accounts to see how our software holds up as accounts age and grow more complex and the interactions between these gradually aging accounts. All right, so takeaways. Here's some takeaways for you to take back to your teams and to take with you after the conference is done. So my biggest regret when working on this project is not recognizing sooner that it was a larger than one-person effort. So there's no reason why I had to Frodo this all the way to Mount Doom on my own. Not only does this spread out the workload, it just makes for better code and easier planning. It also means you don't have to write a billion wiki pages and Slack updates, which brings me to my next point. The people really want to help. So from the time the project was just a gleam in my eye all the way up until the last test, I had people lining up to help. But I always politely declined because I didn't want to add to their workload. I didn't want to impose more work on them. So I learned the hard way that when people are offering to help, the only downside is accepting the 5 to 10 minutes it takes to get them up to speed. So when you're sharing the load with people that really want to help, it'll let you get some rest. So the pressure of running these tests combined with being sleep deprived just made it more difficult to come up with solutions on the fly when problems did arise. It seems obvious, but when you're well rested, you're going to make better decisions and you're less likely to burn out. You'll also be way less of a jerk to your teammates. So although we learned some really useful things about our capacity and ended up with a nifty load generation platform, and although I personally learned way more than I thought over the past few months, I somehow lost sight of what it means to be part of an engineering team, an engineering department, and an organization that's committed to collaboration and learning. So really, I owe each of my colleagues a huge thank you for their support and often for just telling me to go home and sleep. Uptime and reliability are the foundations of what we do, and I love ripping things apart in order to put them back together stronger, smarter, and more resilient than when we started. Thanks.
All right, we have a microphone up front for any questions. Please come forward and ask Renee all the things.
Maybe not all the things. I mean, we got 8 minutes.
So you kind of glossed over something that I found really astounding, which was you said something along the lines of, so our first 2 tests had moderately significant customer impact. How did you convince people to even do a second test after you had moderately significant customer impact on the first one? Like, why did they not just say, we're walking away from this, we can't do this?
That's a really, really good question. And, well, let's be honest here. I definitely I had scheduled a third one, and then I got like a ping on Slack from my engineering manager and was like, hey, Renee, can we chat for a few minutes? And so we talked it over, and we looked at the parameters of the third test and decided that, okay, let's avoid impacting this one system because we already know that we need to work on it. There's no point in just piling the shit onto this one team over and over again. And let's get the leads on the other teams to vet the plan. And so again, this goes back to collaboration and having it checked by other people and getting input from other people and their expertise. And I have to give credit to the execs and the engineering department for believing in this and being like, all right, you fucked up twice, but this time, let's cross our fingers and hope that a group of you won't mess it up as bad. Yeah.
I honestly don't mean this in a snarky way. I'm legitimately curious. Why is production not the same as staging such that you can usefully test without taking down prod? And have you factored that into further work to say how can we make staging more like prod?
Okay. Actually, that's also a really good question. So one of the reasons why our staging and load test environments aren't the same as prod is that we are constantly processing events and sending out notifications on our production systems. PagerDuty is a 24/7 sort of thing. So when we're running our tests, we're running our tests at the same time as all the other regular account activity is going on. So from your tiny little mom and pop shops with 2 people on call to bigger organizations that have thousands of users, all these things are still active as we're going on. That it's just not the same when we are looking looking at staging or load tests. So this isn't exactly a controlled experiment because we kind of need that background noise to really see what the effects of a single very active account would be, what the effects would be as all that other stuff is going on at the same time. I hope that answers your question. So.
Hello, thank you very much for an interesting talk. You have mentioned about the Chaos Monkey from Netflix. What you have told us about is not exactly an equivalent, right? So you tested basically the high influx of the events. But do you now have plans to implement chaos engineering inside the production infrastructure as it is like in Netflix or other companies who use this?
Actually, yeah, we actually do. We have Chaos Kitten. Chaos Cat. If you wanna work on Chaos Cat, then you extend it. I think there's like a module that's called Chaos Kitten, and then like you have to get it vetted and stuff before it gets merged into Chaos Cat. But Chaos Cat kind of does the same thing. It's like an ongoing kind of like low-level failure Friday where it just like restarts boxes every once in a while. So yeah, every once in a while, a bunch of us gets paged because Chaos Cat restarted something that was like not supposed to be restarted. But the thing about using this internal tool is that it allows like really fine-tuned control on whitelists for like what we are going to be like testing continuously during the day. So it's all done through chat ops. It's like I think it's actually kill the cat, like kill Chaos Cat and stuff like that. It's kind of morbid. I didn't do it. Some other people did. Yeah. Any other questions?
All right, well, let's give Renee a great big round of applause for her awesome talk.